Hello and welcome back to Manifolds, the video series where we talk a lot about the integration on generalized surfaces. And in today's part 59, we will look at Stokes' integral theorem again and consider an example of it. And in fact, this will be the closure of this video series, so the last video in the course Manifolds. However, as always, before we go into the topic of today, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. I'm really grateful for all the support, because your support made this video course here possible. And now without further ado, I can immediately tell you the motivation of the example of today, because it also comes from physics. Indeed, it's about the magnetic field that is associated to an electric current. We can just imagine an infinite wire where we have a constant electric current I. And now physics tells us that around such a wire, a constant magnetic field B occurs. So you see, this magnetic field B is a vector field in R3. And this is the vector field we want to consider in Stokes' integral theorem. But maybe first I should tell you the physical formula here. So we have the current I in the numerator and 2 pi in the denominator. And then something comes in that we call the magnetic constant, and it's denoted by μ0. This one carries some physical units, which means from the mathematical point of view, we can set it to 1. In other words, all the things here in the front are constant anyway, and now comes the part where we see how the magnetic field varies in space. And indeed, it's weaker the further we are away from our wire. So for any point in the space, we measure the minimal distance to the wire and call it capital R. And exactly this distance we put in the denominator. So this will be the magnitude of our magnetic field, but it also has direction, so we have to multiply with a 3-dimensional vector as well. And it's perpendicular to the direction of the current, which means here in the third component we have a 0. And the first and the second coordinates are flipped, so we have minus y and plus x. And since we want to have a unit vector here, we also have to divide by the length of this vector, which obviously is our length r again, so we actually have 1 over r squared in the denominator. And that's it. This is the physical law from electromagnetism, which is our motivation for the example of today. Which means now we go to the mathematics and just consider a mathematical vector field well defined on R3. And as always, we just call it V, and now we can use the definition from above, which already tells us that we have to exclude the points on the wire itself, which simply excludes the cases that the first and the second coordinates are equal to 0. So you could just say that W here is given by the z-axis. So there we have 0, 0, and then any other number x3. So these are exactly the points in space we don't consider. All the other ones are fine, and there we can define v of x. And we see if we ignore all the constants, we just have 1 over the distance to the z-axis. And if we also square this distance, we just have x1 squared plus x2 squared. And then the whole thing times the 3-dimensional vector as before. So in our setting, minus x2 plus x1 and 0. So this is the vector field we consider now. And since we already know we want to apply Stokes' integral theorem, we can look at the curl of V as well. And there I should know that the curl is also a 3-dimensional vector field. So for every point in the domain of definition, we can define a 3-dimensional vector. And there please recall the definition of it. The curl of V is given by this combination of the partial derivatives. And this is quite helpful already, because as we can see here and there, we have the third component of V3 involved, which is already equal to 0. And moreover, also here and there we get a 0, because we have the partial derivative with respect to x3, which is not involved in the formulation there. In other words, we immediately get that the first 2 components have to vanish. So we only have to do a calculation for the third component. And this should not be so hard, because we only have 2 partial derivatives there. So let's immediately start with the partial derivative of the second component of v with respect to x1. This means here we have a fraction where plus x1 is in the numerator. And the denominator is the same as before, and the whole thing tells us what can help us here is the quotient rule of differentiation, which simply tells us that we square the denominator and put it to the numerator again. And then we multiply it with the derivative of the original numerator, which is just 1 in this case. And then we just have minus and the derivative the other way around, which means we take x1 and the derivative of the original denominator. And as a partial derivative, this is just 2 times x1. And I think this is already good enough. Now let's go to the second partial derivative we have to calculate. This is quite similar, but now we have the first component of v, which is minus x2. And the partial derivative is with respect to x2 as well, which means we can do a similar quotient rule as before. The only difference here is that we have a minus sign involved, but this one we can just pull to the front of the whole fraction. Hence we also just have the derivative 1 minus the other way around. So x2 times 2x2. So this is a nice result, and now we just have to calculate the difference of both results. So we get that this minus sign we have here just becomes a plus sign. And since the denominator is the same anyway, we can just put everything together in the numerator. And indeed, there we immediately recognize that the x1 squares cancel completely and the x2 squares also cancel. In other words, our numerator vanishes and the result here is just 0 as well. So the conclusion is that the curl of v just vanishes everywhere on the domain of definition. So in short, you can just say it's equal to the 0 vector in R3. And obviously this result makes one part in the formula of Stokes' theorem quite nice. And actually, in order to apply Stokes' theorem, we need to consider a two-dimensional manifold with boundary embedded in R3. And as you might already guess, the boundary is not allowed to lie on the z-axis. Indeed, the whole set W is our exceptional set. So for example, you could say this one is our two-dimensional manifold and it lies around our z-axis. And let's call the manifold M tilde with boundary del M tilde. And as already mentioned, the first requirement is that this boundary does not cross the z-axis in any way. So the intersection with W should definitely be empty. However, this is not the only requirement we need here, because we also want to have a flat disk around the z-axis as well in M tilde. This means we can find a small epsilon greater 0, such that the disk with radius epsilon lies completely in M tilde. So x1 and x2 can vary on the disk, but the z-coordinate x3 is fixed. And this is a requirement here because we want to remove this disk from the manifold. This makes sense because we want to have a safe distance epsilon from the singularity of the vector field. And in fact, removing this disk will define our manifold M with two boundaries. And exactly for this new manifold M, we will apply Stokes' integral theorem. So the first step here is to remove the singularity by subtracting the whole disk. So in short, M is defined by M tilde without a disk, which also implies that the boundary of M gets larger than the boundary of M tilde. This is quite clear. We have our original boundary of M tilde and the circle with radius epsilon in the middle. However, here please don't forget, M is an orientated manifold and the orientation is inherited by the boundary. So for example, you could say the positive orientation on the boundary of M tilde is given by these tangent vectors. So this is quite nice, but then the inherited orientation on the inner boundary goes the other way around. If you use the right hand rule for that, it's quite clear because the outward pointing tangent vector from M goes in opposite directions. This is important to remember because the orientation adds a sign in Stokes' integral theorem. And now let's simply apply it to the manifold M. On the left hand side we have the curl of V in the inner product with the unit normal vector field on M. And in order to be consistent with the picture above, the normal vector field would look like this. However, this is not so important because we already know that the left-hand side here is equal to 0 anyway. This means we are more interested on the right-hand side, where we have the integral over the boundary of M. And there we have the vector field v itself in the inner product with the tangent vectors we have already sketched before. Hence, now we can just write that the left-hand side is equal to 0 and the right-hand side is split into two parts. One is the outer boundary and the other one the inner boundary. And maybe to keep it short, let's not give it a name, let's just copy the picture of this circle. And now the implication here is that we can calculate this curve integral over the outer boundary just by calculating this curve integral over the circle. The only difference is a minus sign, but this one we can also absorb into the orientation if we want that. In other words, here we just have to flip the tangent vectors by 180 degrees. And since we just work on the circle here, we can immediately write down the definition of this tangent vector. At a given point we have the coordinates x1 and x2 and we just need to flip them. So we have minus x2 in the first coordinate and then plus x1. So this is the direction of the tangent vector, and now you know we also want to have a unit tangent vector. So we have to divide by the norm of the same vector, which is the square root of x1 squared plus x2 squared. And there you can immediately recognize that this is quite similar to our v vector field itself. In fact, this was exactly given by the same vector, but the square root is not involved, we just have it squared here. So this means the inner product here is quite easy to calculate. Indeed, we just get the norm of the vector squared, which means it completely cancels with the first fraction here. Hence only 1 over the norm remains, and there we know this norm is given by the radius of our circle. So we have a constant as a result, which is 1 over epsilon. And this is really nice, because it means that the integral here on the right hand side is quite easy to solve. Actually, it's just the integral over the volume form of the boundary, which means it gives us the length of this circle. And the circumference formula for a circle you should know, it's simply 2 times pi times the radius, which is epsilon in our case. And there we have it, the result of the whole curve integral is just given by 2 pi. And there you see, it really does not matter for the result what strange path the boundary of M tilde actually takes. As long as we have the assumption that we go around our z-axis, we get out 2 pi. And now obviously, this is also now something you can apply in physics. There, if you consider the curve given as a boundary and our magnetic field B, then the curve integral from before, which in the short notation is just the inner product B with ds, is a constant in this case. And by using the definition of B from before, you see that the constant 2 pi will cancel and only the constant μ0 and the current I remain. And now this physical formula for a constant current in a wire is known as Ampere's law. So you see, this formulation of this law just comes out of the nice theorem by Stokes. And with this last example, the course about manifolds is finished. Obviously, there are still a lot of other related topics we could discuss here, but this will be done in a different video course. Therefore, I really hope that we meet in another video series again, and I wish you a nice day. Bye bye.